Well, welcome everyone. We got lots today, and you're going to learn how to make it possible for your learners to discover Pythagoras' theorem for themselves. They will think that they've invented it or they've discovered it. So I'm Tony. I started AIMSEC about 20 years ago. I've retired from it now, but I'm spending my time on the Global Teacher Empowerment Network and writing resources for you, which are all on the Aiming High website. Caroline.
Hello, everyone. My name's Caroline. I'm the founder of Bubbly Maths. And what we do is, the idea is that every child on earth will love learning and enjoy mathematics. And what better way to do that than work with Tony, reaching teachers all around the world to give them resources to do exactly that. And they will actually be discovering Pythagoras, won't they, Tony? Not for the first time, but they will actually be discovering it.
Yes, yes. And it's great for young learners, year 8, say, to be able to meet it in this way, to meet this big theorem in this way.
Elizabeth.
Hi there, my name's Elizabeth, and you can hear that I've got a slightly different accent from Tony and Caroline. I'm originally from Scotland, but I came to South Africa in 2008 and taught in a local high school in Muizenberg. And after that, I got in touch with AIMS and AIMSEC and became involved with them, and I've been with them ever since.
Well, today you will improve your skills and knowledge and understanding of a few different parts of mathematics, but at the same time you'll learn how to introduce these ideas to your learners. So we'll be playing games strategically. The important word there is strategically. You'll develop visualization, improve your visualization and your ability to work systematically. We'll do some simple work on areas by counting squares and conservation of area. When you move a figure around, unless you squeeze it and squash it or stretch it, the area stays the same. And in mathematics, there's a whole sort of theory about conservation of area. And we've mentioned a couple of times already the discovery by learners of Pythagoras' theorem. But as well as that, we're going to do some work on transformations, and I mean reflections and rotations, and some algebra as well. Well, again, we're thinking about learning in school as on a spiral where year after year, the learners revisit ideas that they've met before, but each time they come to that idea again, they build around it and extend what they know, learn a few new ideas, a few new aspects of that idea, develop it until when they're on the top platform, they're ready to leave school. They know quite a lot about it, but they don't meet things new when they go to secondary school. They should have met them before that in primary, and we are going to be always talking about early years, lower primary, and so on through the various phases until school leaving. And here's the list of the different things we're going to do today. I'm not going to read them out one by one. You'll read them for yourself, but we'll start early on with some paper folding and a game. And we'll have a jigsaw, which will be fun to do, but we'll learn a lot by doing it. And we'll talk about learning objectives at the end. As with all good lessons and workshops, we'll have a summary and we'll talk about what we've learned and what we thought about it.
I'm going to start with investigating a square, some very simple geometry that can be done at any age, because the conversation that follows it is you make it relevant to your group. So I'm going to start with an A4 sheet of paper. If you want to do this, go get yourself an A4 sheet of paper.
You'll see the various stages, but Caroline's going to demonstrate them.
And in case your learners don't know, I don't know if you're aware of the fact, well, at least in the UK, a lot of learners do not know how to make a square from an A4 sheet of paper or any sheet of paper. So we're just going to cover that just in case. So take a corner and fold it along, bisecting the 90-degree corner there. Make a nice sharp fold to make sure you've got it straight, and then fold that over. And you can either fold back and forth, and then rip it off, or use scissors. Here's one I prepared earlier to make sure that I've made a good job of it. Okay, so what the investigation we're going to make, once you've got your squares, so we want that in the original crease as part of this investigation. You've now got a triangle. We're going to examine that in a minute, but first we're going to do in the constructions. We're going to fold that one in half, taking one of the smaller angles across to the other. So we're making it, folding it along that line of symmetry, and now we have a smaller triangle. So this is the investigation. I know you know this, but this is what your learners are going to investigate. We're going to look at this angle here. Now, what can we tell about this angle here? If we open it up, we can see we have 4 angles on our original sheet of paper, and each of those we know that the angle is a right angle, 90 degrees on there. And this one we've bisected twice, so that we have that one's been bisected and that one's been bisected, which means that those 4 angles are the same. In order for those 4 angles to be the same, you're going to divide 360 by 4, which gives you an angle of 90 degrees. We've folded a 360 across once. We know that's 180. Fold it again, half of that is 90 degrees. So that's one thing to look at with your learners. And then the next thing is we've got these other 2 angles. Now, what is the same and what is different about these 2 angles? What do we know about these 2 angles? What can we tell about them? We know that one's down. We now know that one's 90 degrees. And these 2, well, we have been bisecting, and we've been doing symmetrical shapes, which means we know these 2 angles are the same as each other. We know that one's 90 degrees, and these 2 are the same. Total angles in a triangle is 180. Take away the 90, that means that plus that is 90, and these are the same angle because we just keep folding in half. And now, of course, we've got a name for this particular triangle. It's got 2 angles that are the same, 2 edge lengths that are the same. It doesn't matter that that's 90 degrees for this, for naming it. It's an isosceles triangle. So that's the investigation that you do with your learners, but they would think about these things for themselves. So the question you want to ask them is, what do you notice? And then if the next slide is going to show us, so the process to go through is you talk about the square being a regular, it's a regular quadrilateral. And so it's got 4 equal edges, 4 equal angles of 90 degrees. So that's a way to define the square. Each adjacent edge is also of equal length. So all edges are the same length. And then the diagonals of the square are equal, and they bisect each other at right angles. And then the internal angles, these ones, they form 90 degrees. So the opposite edges of a square, which is another point, opposite edges are always parallel. Those are the properties of the square, and those are properties that they can look literally hands-on, get to grips with themselves. This is something they'll be able to remember, and if they're not sure, they can recreate it just by folding a square twice.
Thank you, Caroline. That's lovely. And what your paper square doesn't show you, but what you can see in the diagram here is that the interior angle in the square is 90. Well, you did see that from the paper folding, and you can see from my diagram that the exterior angle is also 90. We're going to play a game, and we want you to decide to be in my team or in Elizabeth's team. We're going to play the Square It game. So the object here is to make a square. I'm going to have red. Oh, and Elizabeth, are you happy with blue?
Yes, thank you, Tony. That'll be fine.
Right. So we're going to play this game, and we're going to, each of us, we're going to try to make a square somewhere or other on this board, which is a 5x5 pin board, or it could be on paper, or it could be using a geoboard. We have A, B, C, D, E along the bottom, and 1, 2, 3, 4, 5. All our moves can be given in terms of these two reference points or coordinates. The red is on E3, and the blue is on D4, as you see it on my slide. And the benefit of this is you can play over the phone. You don't, or you can play without the diagram. You can play in your head without the diagram. You can tell somebody else what your next move is. I'm red and Elizabeth's blue, and Elizabeth is going to go first.
Okay, well, I have a challenge for us. I have orange and green. So Elizabeth is green and Tony is orange. Right, here we go.
So could I go on let's see, B3.
B3 here.
Yep.
Okay. Tony.
Right. Okay, I'm going to go. Oh, you're on B3. Okay, okay. I'm going to go on B5.
B5.
Could I go on, what's this one? Is that, I'll go on B4.
Okay, I will go on okay. I will go on E4.
Can I go on C4?
Well, I'm going to go on C3.
Oh, Tony.
Spoil sport.
Okay.
He's not letting you win.
No, that's for sure. But I'll do my best.
Yeah.
Okay. So is it me again, or is it Tony?
It's Elizabeth.
Okay, so what have I got now? Let's see. Could you just move your pen out the way a wee minute, Caroline, to try and visualize something? Okay, thank you. And I've run out of dots there. Can I go on? A, B, C. Can I go on A, B, C, C3?
C3 is taken.
Okay, D3.
D3.
Yeah, that's the one I meant.
I'm going to go on D1.
D1. Can I go on D2?
You can, and I'm very reluctantly going to put you on D2 because that's where you asked to go. Is that your final answer, Elizabeth?
I think you're suggesting it shouldn't be.
That your final answer, Elizabeth? Sorry, Tony.
I'm
let
not
me-
keen.
Oh, wait a wee minute. Move the pen a wee minute, Caroline, to see what I can do here. Yeah. Oh, no, there isn't. Let me just see what Tony's got here.
Caroline, I mean, Elizabeth, you can go, you can change it. Have another thought, think.
That's what she's doing, Tony.
Yeah, it's just, it's not that easy to see what's happening on this. Right, okay. So do these dots end on, we've only got A, B, C, D, and E, have we?
Yes?
That's correct. There's
Okay.
nothing beyond that.
Right, so let's have a wee look.
The place you were going to go is very warm.
Caroline, why don't you put the dot on?
Practically, I'm going to put Elizabeth. Sorry, Tony. Tony's up to mischief anyway. So
Yeah, you put the dot on for me. There we go.
I'm
That's
going to make a
perfect,
decision for
Caroline.
you.
Thank you.
And Elizabeth, without knowing it,
Yeah.
Where have you put it, Caroline?
can you see it?
No, I can't see it. Where have you put it?
On C2. There.
C2. Oh, and now you've got a square, Elizabeth. Well done.
Yeah,
Caroline
thanks, Caroline.
You're
Square.
welcome. Team effort.
And I didn't see that, and I was thinking of putting mine on A2.
A2. Yeah, Tony would have gone
Yeah,
there.
then
If
you would
put
have
it-
got a
you
solution.
put it
Yeah.
on there, Tony would have put it on here. And for those that are not sure where this square is, it is here. And this is not an easy square to visualize, but it's a very powerful square to visualize. And by the end of this session, you will be very clear on A, that that's a square, and B, how to help your learners know that that's a square and be certain of it.
Well, we're going to play the computer next because you'll be able to see better what's happening. So I'm going to go to the computer now, and this is the Square It game. And here we are. And we're going to opt for, well, it's player 1 human, player 2 is the computer. Caroline, where would you as a human, as player 1, want to go? Remember your A, B, C, D, E, and 1, 2, 3, 4, 5.
Okay, so I'm going to go with A, B, C, D, 1, 2, 3, 4. D4, delta 4.
D4 is here.
Yeah.
And the computer has gone on E4.
I'm doing this. I think Elizabeth and I should do it together. I'm going to go with I'm gonna do a Tony. I'm gonna say A2.
A2 is here.
That's A3, but it's too late now.
No,
Okay.
it's A3. Sorry, it is A3.
All right. Well, I'll go with A3. We're playing with that. Okay, all right then. Here we go. I'm going with this is quite fun actually. Something I was thinking of earlier. I'm going to go with a C6. C6. So don't click it until I confirm you're in the right place. Yes. And now.
No, just let's ask the audience.
Oh, okay. All right. Well, don't click.
Where should Caroline go now? Because clearly we don't want the computer to win.
Janita says C2.
Absolutely, yes.
Yes, 2.
Where should we go next? Well, they went on B5, Okay, because if we'd gone on B5, we would have got a square. Our square would have looked like this.
Yeah.
So where are we going to go now?
We could just go there,
Where?
where the mouse is.
Oh, the mouse is on E1.
If we don't play it in the correct place, we will.
Lose.
Yeah, we'll get something here,
D3.
D3.
D3 is
D3.
D3 is here.
Chaba and Lucien both say D3.
And can you see the computer has gone on F4? Again, they're going to make a square if we're not careful. F5.
F5.
We should go.
Is it F5? Oh, we've lost. I think we've lost. Yeah, we've lost. Yeah.
Well, had we
even
not
if-
gone on
even if- no,
F5, they would have got, had we not gone on F5, they would have got this square. But what the computer did was it had it prepared
yeah.
two squares and we could only stop one. So it's very much a game of strategy and a lot of fun, of course. You have to be online to play it. It's a live game that Enrich have put up, and you have to be online to play it. But you can play it against another person, and you can play it in two teams in your lesson, and either as a people mass game or using your chalkboard to put the dots on the board, and then two teams, rather as we did just now with Elizabeth's team and my team. And then the learners can play in pairs by just drawing their own grids. Here you see another game. It's a people mass game. And you might like to do this with your learners. You need chairs, and here they're set out for a game with just a 4x4 grid. It's exactly the same game, only here you need two teams, and you can have the people in each team talking to each other about which chair to take next. They take it in turns to sit on one of the team to sit on a chair, and they're trying to make a square. So there's one square they might have made. Can you see those four chairs? Here's another square they might have made, perhaps a more obvious one. Now you can prove that these angles in this blue tilted square are right angles, because what you have on the red corners is a right angled triangle with a blue hypotenuse, and each of these triangles are 2 by 1, and the blue hypotenuse making up the third side, 2 by 1 again, and 2 by 1 again. So they're congruent triangles, and the angles are 90 degrees at the corners. We're not disputing that, because that's the way the game is laid out. And in this right angled triangle, the two angles together add up to 90. And this angle here, this angle, can you see the one I'm indicating with my cursor? That angle equals that angle. So on this edge here, these two angles add up to 90 because they're the same as the two angles in the triangles. And if they add up to 90, and since your learners know that the angles in a straight line add up to 180 degrees, the red line is a straight line, those two angles add up to 90, so the angle in here is 90. So we've got the fact that the edges are the same length because they're the corresponding edges of 4 congruent triangles. And we've now shown that the angles are 90 degrees.
So I'm going to just talk for a minute or two about geoboards. A geoboard is a square block of wood, as you can see on the picture here, with nails hammered in at regular intervals. And if you ever come to one of our face-to-face courses, you will actually make one of these geoboards at the course. So it's quite a noisy session. Everybody gets their piece of wood, they get their hammer and nails, and they hammer in the nails at regular intervals, and then we use the geoboards on the course. Part of the nail sticks out from the wood so that rubber bands can be wrapped around them to make shapes, as you can see on the one on the screen here. This is useful when teaching things like perimeter, area of two-dimensional shapes. You can also identify the properties of two-dimensional shapes, for example, triangles, squares, rectangles, and polygons. And Tony will now show you some activities which you can do on the geoboard.
Okay, and lots of these are on the Aiming High website. So here you see dots on a piece of paper, and everything that you do with a geoboard you can do on paper, but you can make these squares and other shapes quickly on a geoboard. Now, answer these questions. You can use the worksheet if you like. If you've got it, if you've printed it out, how many pins are there on the geoboard in the diagram? It's 25. Okay. The small square, calling that 1 square unit. So how many square units are there in the geoboard you see on the slide? How many square units? That's 16. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now, the red square you see there is made by joining the middle points on the outer edges. What's the area of the red square in square units? 9, Lucian says. The answer is actually 8. It's actually half, the area of the red square is half the area, which is 16 in total on the geoboard. And what you see is that, in fact, you could fold, if you did it on paper, you could fold this square to the middle, and this square could also be folded to the middle. On the outside, you've got 4 congruent triangles, and each one of them is made up of 2 units. Each one of them's 2 units. So you've got the whole of the red square, 16 units, take away 8 units, giving you 8. And asking you to explain your answer, I hope you ask your learners to explain their answers. And there are all sorts of different ways to explain how you get that answer.
You can see that these are all squares. What are the areas of the 3 squares? Well, looking at the first one here, area 4, we've got, you can see that there's 4 squares, so the area is 4 square units. In this one here, you can see there's a square in the middle, and then we've got a rectangle which has got a diagonal through it. So as you know from geometry, that means that's half of the rectangle, so that will be 1 square. So we've got 1 in the middle, 1 here, 1 here, 1 here, and 1 here. So that gives us our area of 5. And then looking at the last one over here, we can see clearly the 4 in the center of the shape. So that's 4. And then it's just a bit similar to the last one there. We've got a rectangle, and half of it has been cut out. So that's 1 for each of those sides. So we've got 4 in the middle and 1 for each of the sides. So that gives you area 8. And I think is there anything else to come up?
Make an area of 2 square units.
So now we want to know how many squares you can make with those 9 pins, and what are their areas.
And so here's the answer. There are actually 6. We can do that with 16 or 25 or 36, any number of dots. And there's the simple, well, a very simple case with the 9 dots. So we can see one square has an area of 4 square units. There are 4 of them with an area of 1 square unit, and one of them, this one here, with an area of 2 square units. We want to challenge you to solve the same puzzle with 16 pins, and we'll tell you for free that there are 20 squares. Can you find them all and their areas? And for 25 pins, there are 50 squares. And can you find them all? And what are the areas now of these 50 squares? It's a very nice problem, and one that your learners will enjoy doing. So we can recommend it. What we've seen this afternoon is we've built up gradually to the idea of these tilted squares and recognizing squares where they're not the lines horizontal and vertical. So here's what we call a poster, and you can use these posters on your classroom wall, or if you want to, you can project them. I mean, if you've got a data projector in your classroom, and they can be used to start your lesson as lesson starters. We've got a lesson starter like this every day on the AIMSEC Facebook page. Now, here's the problem we've just been discussing. It's the how many squares problem. And we're asking how many with 4 dots, how many with 9, 16, and 25 dots. It's the same problem. Now, if you put this up for a lesson starter and just, you could do it as a routine every day. And when the learners come in, they should sit down immediately, not chatting, quietly sit down and start the activity. It's there up on the board. They may choose to play the game. It's in the sort of pink side panel here, or they may start counting squares. So there it is. That's one of our posters.
So this is a jigsaw puzzle that you can play with younger learners. This is simply experiencing Pythagoras, which you would introduce later on in life, but having the experience of doing this is a really valuable way of starting up on that learning spiral and just experiencing squares and triangles and what you can do with them. Or you can just draw it. With young children, what you do is you jumble up the shapes and you fit them into a frame, which you'll see on the worksheet, and there are different ways of solving it. But you can put it on in one way, take the pieces off, and then let the learners put them back on just to recreate it. That's with young children. As they get older, or as they have more experience, they themselves can cut out the pieces. Now I've just got a little demonstration here. They can cut out the template that you've got from here, or they can make their own, which you can do as they get more experience. You start with any triangle. I've just drawn a triangle here on square paper. Any triangle, take that triangle and make all the shapes that match that triangle. So I've done this, and again here I've made a little triangle, and then I've made do 4 of those, and then a square that matches the shorter end, a square that matches the longer, and then you make one that matches the length of the hypotenuse, which is the one at the top. Now I've got the pieces of the puzzle here, and the learners can move them around, manipulate them, see how they can make them fit into a larger square. So they've got to match. So these two match there, and that goes there. They've got to make a square in the end. So those two match there, and hey presto, I've sort of made one solution of the puzzle. Now the square you want to fit it in is that size. And that's the sort of activity, it's just a jigsaw puzzle. It's for the learners to experience this before they ever encounter Pythagoras. So when it comes time to introduce it, they're comfortable with the vocabulary, with the length of how the triangles and the squares match together.
At one point, Caroline said there, any triangle. Of course, it wasn't any triangle.
Any
It's
right-angled
right
triangle, sorry.
But what is important is that it can be any right-angled triangle, and ideally, and Elizabeth will explain it now, it's each learner will have their own right-angled triangle that is different from all the others, and they'll see that the jigsaw is you can always solve their jigsaw whatever shape their right-angled triangle is.
So you have to use scrap paper or card, but it must have right angles at the corners. So you start with any right angled triangle and you give the edges names. So the shortest edge, which is this one here, that would be B. And the base here is A. And the longest edge, which is this one here, is C. So you have to make 4 identical or congruent, which means the same thing, 4 congruent triangles like this. Then you have to use the corners of a piece of paper to give you right angles. So you would get your right angle by using the corner of the piece of paper, that's this part here. And to make the drawing more accurate, make a pinprick to mark a point before drawing the line. Okay, so you would use a pinprick. So now we have to make the squares that are going to go on to your right angled triangle. So use the first triangle that you make to give you the length for the edges of the 3 squares. So you've got your triangle. If you line up your piece of paper with side A, you would put a pinprick at each part to get the length of the square. And then you would do the same so that you've got all the different parts you need to cut out the square, and that fits onto part A. You would do the same to get the square which would match on to side B. So each side of the square is obviously B, and then the same for the square that tilts on its side and goes on side C. Okay.
Excellent. And depending on the age of the learners and the grade you're teaching, you can choose whether to give them something to cut it out for them, to give them pieces to cut out. But there isn't just one puzzle here. There are actually 2 different puzzles. They're described there. You've got to either fit 5 of the pieces together to make a square, or you've got to fit 6 of the pieces together to make a square, and you've got to find which pieces, of course. Caroline showed you one solution, but there are several different solutions. I seem to remember she used 6 pieces. So how about trying to use 5 pieces? Putting your pieces into the frame. Now there's a frame there, and whichever solution you actually come up with, it will fit into that frame. Did you get either of these solutions? You see, they both fit in the frame below, and the one on the left with a pink square has got 5 pieces, and the one on the right with the green and orange squares has got 6 pieces, and the total area within the frame, of course, is the same. And so immediately, what can you see? Here are the key questions. Let's think about these questions. The first one is, what do you notice about these 2 solutions? And you know the angles in the triangles. How do you know the frame has got right angles at the corners? The third question is, what do you know about the lengths of the edges of the squares and of the edges of the triangles? Well, do you remember that Elizabeth suggested we call the edges of the triangle the shorter leg B, the longer one A, and the diagonal C, the hypotenuse of the right angle triangle C. So it's the edge of the pink square there, that's C. If you put the four triangles in position for solution one, this one, if you put the four triangles into the frame and there's a empty space in the middle, what can you say about the space left uncovered? Well, it's the area of the whole frame minus or less the area of the four blue squares. The pink square is the area of the frame, let's subtract the area of the four triangles. What's the area of that space? Well, we know it's c squared because we have got this edge. Hypotenuse of the right-angled triangle is C. So if you move the four triangles into the position in solution 2, where one pair makes a rectangle here on the top right, and the other pair makes a rectangle at the bottom left there, then what can you say if you put those down here? So you've only got four triangles in this frame, and there's a space at this corner and another space here. What can you say about the space left uncovered? Well, it's a space which would be covered by the blue and the orange squares between them, and it must be the area of the whole outer frame minus the four blue triangles. And so you've got those two areas. Let's go back. You've got the area of the frame minus the four blue triangles is c squared. The area of the frame minus the two smaller triangles is a squared plus b squared. What does that tell you? Now here you see three solutions. Can you see the difference between solution 2 and solution 3? In solution 3, the blue triangles make two rectangles which make a sort of L shape. And below you see the reflections of those solutions. But there are essentially only three solutions that are completely different from each other. We've numbered them 1, 2, and 3. And on this diagram, we show the reflections. So what do you notice about the 6 diagrams, and what transformations can you see between one diagram and another? I've mentioned the reflection, but there are other transformations that you can see in that picture. Why does the heading say there are only 3 solutions? I mean, you might have found a different one, or one that looks different. When you look at your solution and what you see on the slide, is it really different, or is it one of these 1, 2, and 3? There are only 3 solutions. Now, this is an easy one. You should get plenty of response from your learners when you ask these questions. What's the same and what's different about the solutions? What's the same and what's different about the solutions? Lots of things you can say about that. Pretty obvious. Just a notice there. And you can show different yes, you can draw different diagrams showing other transformations of the 3 solutions.
there are 14 variations, only 3 types. So you've just seen those 3 on their own, but if you look at all the different combinations, and this is a great activity to do with the learners, you can make a poster and discuss, have them discuss and explain why there are only actually 3 solutions, and what is the question you had in the last one, what's the same and what's different about them, why are they part of the same solution. Use the vocabulary rotation and reflection. The solution 1, is there a reflection? Is there a rotation? Solution 2, there are lots of variations. There's only 2 variations of solution 1. Why are there only 2 variations of solution 1? So much wonderful discussion about symmetry at the same time as getting experiencing the properties of a right angle triangle. They're solid on this. It's going to help them so much when it comes to the next phase.
Yes, and of course, in the curriculum, you have got to teach about reflections and rotations, and so this is actually covering a lot of different ideas that you need to be teaching.
Let's have a look at this slide now. It says we have to work out the length of the edges of the outer frame. So let's look at the outer frame. Here's the outer frame here. So the length of the edges. So we can see that this top edge here is B plus A. And this one coming down here is also B plus A. So it's a square because it's sides all the same length. They're all B plus A on the outside. So let's put that in. For length of edges of outer frame, can we put in B plus A? Thank you. So what will the area of the outer frame be? If the length is A plus B times A plus B, what will that area give us? We do have someone who's given us an answer. They've put A plus B in the bracket to the power 2. That is correct. So what would be the area of the yellow square now? And the area of the green square?
B squared, yes, thanks, Lucian.
So the total area of the 4 triangles, what will that be?
And there are 4 of them, and the pairs, they make rectangles. So it's quite easy to find the area. Now, what we've got is A squared plus B squared plus 2AB, which is the total area of everything you see, all the coloured pieces, the 6 coloured pieces. Just the 4 triangles alone, each rectangle is of area AB, so you've got 2AB.
Okay.
Next question. We want to work that out.
So the conclusion then, we've worked it out for, so A plus B squared, that's the outside of this shape. A plus B squared is going to be A squared plus B squared plus 2AB, because we've worked out the area of the different parts. So there's your next thing to work out. From this solution to the puzzle, use the fact that the area of the 4 squares is 2AB. What is the remaining area of the pink square?
Lucian says A squared plus B squared.
Yeah. Thank you, Lucian. That's perfect.
That's the pink square is, of course, edge C. So what have we proved? Painlessly, we found out that C squared is A squared plus B squared. And of course, as teachers, you know that's Pythagoras' theorem. But your learners will be able to find that out for themselves. And learners who haven't ever heard of Pythagoras, just by doing this jigsaw. So it's worth spending some time on it, because my experience is that if they learn it this way, they'll never forget it. So I'd love to hear if you do use the methods, or this method, or any other one of our AIMSEC methods in your classroom. We'd just love to hear about it.
What are the objectives? What are we looking to do here? get to a point where they actually understand Pythagoras, and it's not just, oh, a squared plus b squared equals c squared, with no further meaning behind it. So give depth in the understanding of Pythagoras, but they'll be able to, with the paper folding, they're reviewing properties about a square, defining the square, again, demystifying everything, making it not a rote learning, but a process of understanding geometry, and develop the understanding of the area. So all those dots and the little squares and finding all the different areas, and then actually finding all the squares and then calculating their areas and explaining why, all develops understanding. And without mentioning Pythagoras at all, they're thinking mathematically about triangles, squares, their areas, how they work together, and to actually discover Pythagoras' theorem for themselves. So they've got the concept, they know that a squared plus b squared equals c squared, they can imagine it, they can visualize it, and then, hey presto, you know what? This fella from way back when actually discovered it, and we call it, what you just discovered, we call Pythagoras' theorem. And in addition to that, you've got the understanding of symmetry, reflection, and rotation, all built into this one exercise. I absolutely love it. So the generic competencies, the visualization skills, they have to work systematically to find all the squares. They have to collaborate to identify all the symmetries and which solutions are unique, and both systematically and collaboratively to find all possible solutions. Tony.
So I think Caroline's given you a few reasons why we should do this activity. It, as we said several times, provides a visual proof of Pythagoras' theorem, suitable for learners from upper primary right through to the school leaving year. The activities should be used early to lay the foundation for work on Pythagoras' theorem before the learners meet the theorem. Now, these are low entry point, high ceiling learning activities. Everybody in your class will be able to do the jigsaw, the make squares jigsaw, and probably find more than one solution. That's the low entry point. It's high ceiling insofar as they should be able to write the proof of Pythagoras' theorem by the time they've worked through everything we've talked about this afternoon. And these learning activities provide challenges to allow for differentiation and inclusion in your lessons then. So whichever age group you're teaching, this is ideal for grade 8. You can offer those who are struggling with mathematics some success in the lesson, and those who are really high flyers, you can give them challenge, and they should be able to go to reach the high ceiling. The proof only requires a little simple reasoning and very little knowledge. You just got to know that the angles of a triangle add up to 180 and the angles on a straight line add up to 180. And you've got to know the area of a square is equal to the square of the length of one edge. Simple, pretty simple as that. As every good lesson should, this is going to end with a summary and some questions and answers and some discussion. Now, what I recommend at the end of a lesson is you ask the learners, what have you learnt this lesson? And you write a list of what's been learnt on the board, and you might add to that list, but a lot of the points you hope will come from the learners themselves. So I'm going to quickly, one by one, put up a little diagram of a few words to summarize what we've done. So we've got the paper folding activity, the square it game, which we played on paper with paper and pencil and also against the computer. We have talked about the people maths, where you could do the same game, but using chairs. we talked about the area of squares and based on 1 unit, but using subtraction to find the areas. We talked about geoboards and how many squares of different sizes you could make on the geoboard. We talked about the jigsaw and the solutions of the jigsaw and how you put all that together to get a squared plus b squared equals c squared.
I'm going to kick it off by just talking about the 4x4, the areas. We found when we were talking about it before the session that that all of us, Tony, Elizabeth, and I, all had a different way of working out that area 5, the area 5 that you see in the bottom left there. Each one, Tony was doing it, it was a different shape, but Tony was doing it by subtracting. Have you seen that? I did it by looking at each square and saw that each square was actually split identically. So I figured that by putting 2 of those squares together, it would add up. Basically, the 2 shapes would add up to 1 because each square, even though if it was rotated, or it's the same. So the little triangle plus the quadrilateral adds up to 1. So that was my 1 unit, and Elizabeth did it differently. So all your learners, but there'll be several different solutions that your learners themselves work out when doing that problem. It's really useful to get them to express that for everybody.
I just wanted to comment that, you know, as teachers, sometimes, you know, we've got the way that we think something should be worked out, and we've got that in our head when we go in to do the lesson. So you have to be open to the fact that there are often more than one ways of doing something, and that if some learner in front of you comes and says something that is correct, you can't sort of say, oh no, I didn't want to like introduce that to the class in cases it confuses them or whatever. You must encourage the learners to come forth and give them their ideas of how to solve the problem, even if it's not the way you were going to teach it to them. You have to sort of encompass all the possible ways of getting the same solution.
I do recommend you to go to our what we call the YouTube channel, the AIMSET YouTube channel. We call it Maths Toys. There are many, many different workshops there that you can replay and watch. If you're going to teach a topic, you might well find one of our workshops has covered that topic, introduced quite a lot of activities for that topic. And so you may want to watch some of the earlier videos from other workshops. And of course, I must say, I just love this Make Squares jigsaw because it's so simple. I mean, it's a very simple jigsaw with different solutions, and you can give it to a 4-year-old. You know, if you're giving it to a 4-year-old, you'd probably give them the pieces and a frame to put them in. But my children, my husband made them for my children. My children were doing jigsaws like that when they were 3. You know, he made them out of wood for them, and so the one you see, which is the number 1 solution here. What we did, we put the 4 triangles in the corners and the big red square, pink square in the middle, and then take the pieces out and say to our children, Francis, you have a go at that. Yvonne, have a go at this. Can you do that? And even at the age of 3, they would do that, you know. And similarly, if you gave them the 6 pieces, the 4 triangles and the green and an orange square, and fitted those in, a very small child could do those. So certainly in your nursery classroom, these could be puzzles that the children could do. But it's got so much, it's really loaded with mathematics, isn't it? It's got so much mathematics in it that it shouts at you in a way. It shouts Pythagoras at you in a way. I don't know whether anybody else has that when it's made that impression on anybody else. But I would, as I said, really love to hear if you do use this with your learners in any of your lessons. This, by the way, is only one of many. There are many proofs of Pythagoras' theorem. There are quite a few jigsaw proofs apart from this one. And if you look on the Aiming High website, you will find the other proofs, some of the other proofs that can be done through just putting pieces together in a jigsaw. And they're not 1,000-piece jigsaws. These are only 5-piece or 6-piece jigsaws here.
These are your resources. These are your links. You will get the links in a PDF as well. And the Square It game, different formats for the Square It game, follow-up activities with the Square It game, the how many squares, and the jigsaw. All of these aren't just links to do what we've done today. These are links that have a lot of other resources behind them, ideas for your lessons, key questions, all kinds of things. This also has the link to the professional development, collaborative learning packs that you can take in and do with your colleagues. And nobody's in charge, nobody's teaching, everyone's learning together. And these are all the links for the various different Aiming High resources. Please use them and make comments on the pages to for your other colleagues to let us know how you've done them, how they've helped, what extra ideas you've had, because you've always got other ideas that aren't already covered in the sessions. And as Tony's already mentioned, the YouTube channel on that, all the GTEN sessions that have been edited so far are all on there. You can go back looking for the topic that we've covered before, and you can find a lot of the videos on there. We're getting to the point where they're all on, all the back the videos are on. And of course the AIMSEC Facebook page, every single day of the year, 365 days a year, there's an idea for you. You just go through the whole AIMSEC Facebook page and just look for just little snippets which then have a link which can take you to doing. You can use them as starters, you can use them as a brief introductory activity, and then go in, click on it, and go into the AIMSEC resource. That will give you, on the Aiming High website, that will give you so much more to do with them. You can apply on there. You want to join, you want to let a colleague know, add a colleague to either going on the AIMSEC course yourselves, or to join us on the GTEN. You've got an email address there to share with them.
The Global Maths and Science lesson, which indeed will be on learning through play, playful learning. We're just about to publish, it should come out in March, our AIMSEC book, Let's Play Mathematically. Now, this is very important for you as teachers because research, there's been quite a lot of research on this, has shown that learners who learn through play learn more, learn faster, do better in school tests and exams, and that is borne out by one country as an example of that is Finland, where they do best in the international comparisons at mathematics, or in the top 5 every year, every time these tests are run. So you should be thinking about your learners are just as capable as anybody anywhere else in the world, and AIMSEC has a lot of good methods to offer you, and amongst them are learning through play. Now, our book is actually, we call these Aiming High family games, and they can be played at home. And the first book is coming out, but also there was a parallel teacher's book coming out in September. And then there will be games for the classroom, which will be just presented in a slightly different way to the family games book. But we'll show you, we'll have a lot of advice and support for teachers as to how to use games in your lessons to help learners to learn, to help them to do better at mathematics, to change attitudes to mathematics. If they have a negative attitude that they think, oh, I can't do it, through learning, through play, they will actually change their minds and decide that actually maths isn't so bad after all, and they can do it. And if they've been frightened of mathematics, maths phobia, it's often described as, they can get over that fear if the teacher produces these ideas of playful learning, which the children will think of as games, but actually there's a lot of very serious learning objectives behind them. You're not going to waste time doing this. You're going to gain time because your learners will learn more quickly, and have a deeper understanding. These games are all available on the Aiming High website as well. I'm busy writing the teacher's notes for them and the inclusion guides. Tell other teachers about this GTEN workshop and the 30-minute maths and science lesson, the GMSL, that's in October, where we have the order of, and we're trying this year to beat our record, 50,000 participants from around the world. So it's time for goodbyes from us. We hope you've gained from it, and thank you for coming along and joining us.
Thank you, everyone. It's been an absolute pleasure. Thank you for the participation, and thank you for just being here. Let us know where you use these things, how it works for you, how it's helped you, how it's helped others.
And from me, just to say thank you to Tony and Caroline for inviting me on. I've really enjoyed it. And thank you for you teachers that have come on this evening and taken part and participated. It's been great. And yeah, see you again sometime.
Bye.
See you in
Bye.
2 weeks. Bye-bye.
Bye.
Bye-bye.
This is a Global Teacher Empowerment Network video collaborating with AIMSEC and the Aiming High website. Our mission is to benefit children in disadvantaged communities all over the world by empowering the teachers who teach them mathematics.